Welcome to the Sleepy Atom, where questions are more comforting than answers, and space is less about stars and more about silence. Tonight we're going to float far beyond the tick-tock rhythm of clocks and enter a world where time slips. In deep space, the very thing we depend on to measure our lives becomes strange, stretchy, quiet, and sometimes missing altogether. Time in space doesn't behave the way you think it does. So take a deep breath, get cozy, and let's begin our long drift through the illusion of time, not with a bang, but with a soft sigh. A clock floating in silence. Imagine a clock, the kind that ticks in a grandmother's kitchen. Now imagine it floating alone, thousands of miles from anything, suspended in the dark silence of space. No wind, no footsteps, no heartbeat nearby to notice the passing seconds. Would the clock still tick? Would time still move in that place? The answer is not as straightforward as it seems. In deep space, without gravity tugging on its gears or sunlight nudging its shadows, a clock behaves differently. According to Einstein's theory of relativity, time isn't fixed. It bends and stretches depending on speed and gravity. So, a clock drifting slowly in empty space would tick differently than one sitting on your desk right now. But here's where it becomes stranger. You, the observer, shape what time looks like. Two identical clocks in different places will disagree. If one is near a massive object like a star, its ticking slows down. The clock doesn't break. It's just obeying space-time's curved laws. In space, time is more like taffy than a ruler, soft, elastic, and always relative. So when we ask what time it is in space, the answer is always, it depends. It depends on where you are, how fast you're moving, and how much gravity is tugging on you. Suddenly, time is no longer universal. It's personal. Each object in the universe lives inside its own pocket of time, its own tempo. This alone turns our idea of time upside down. If time isn't the same everywhere, then maybe it was never real in the first place. Or maybe it's more real than anything else because it's experienced, not measured. Ahead in this video, we'll see how space doesn't just twist light, it twists time itself. The deeper you go, the slower it gets. Imagine walking down a hill, but the hill is made of time. Each step downward makes your minutes stretch just a little bit longer. This isn't fantasy, it's gravity. The stronger the pull of gravity, the slower time moves. This is called gravitational time dilation, and it's been tested over and over again. Even on Earth, clocks at sea level tick a little slower than clocks on mountaintops. It's not something you'd notice day to day. But the deeper into a gravitational well you go, say, near a black hole, the difference becomes extreme. Time doesn't just slow, it nearly stops. If you stood at the edge of a black hole while a friend stayed far away, you'd both feel time moving normally. But later, when you met again, you'd have aged just minutes, and your friend could be decades older. This is not science fiction. It's the natural stretching of time in strong gravity. What's beautiful and eerie is that the experience feels normal from within. You wouldn't feel your own time slowing down. You'd feel like everything else is speeding past. This quiet separation of realities is one of the great paradoxes of space. Time is local, even when space is vast. And so, the deeper you fall into gravity, the more slowly the world outside seems to spin. You're not broken. You're just in a slower version of now. In the next part of our journey, we'll ask, if time can slow, can it ever stop? Can time actually stop? Let's play with an idea that feels impossible. What if time could stop? Not for everyone, just for you. Could there be a place or a condition where your clock freezes entirely and the universe carries on without you? It sounds like a paradox, But in physics, it's not only possible, it might already be happening. At the very edge of a black hole lies a place called the event horizon. It's not a wall, it's a moment. Cross it and light itself can't escape. And if light can't leave, time, as we know it, can't tick. From the outside you seem frozen, suspended at the brink of nothingness. But from your perspective, if you were falling in, time would feel perfectly normal. Your heart would beat, you'd blink, you'd fall. But the outside universe would speed up so much that it might age thousands of years in a blink. The stars would spin, galaxies would stretch, and you would remain in your moment. This separation between experience and observation is what makes space so quietly terrifying and mesmerizing. Time doesn't stop absolutely, it stops relatively. From one angle you're paused, from another you're still in motion. So, is stopped time still time at all? These questions don't have easy answers, but they're not meant to frighten. They're meant to slow us down, and maybe even comfort us. In the strange corners of space, stillness and movement are the same thing, just seen from different eyes. And now we wonder, is there a way to reverse this? Backwards through time? When we think of time, we think of it as a line, forward only. But deep space has other ideas. Under certain conditions, mathematically speaking, the universe allows for loops. These loops aren't just in space, they bend time back on itself. Theoretically, you could return to a moment, not just a place. There's a concept in general relativity called a closed time-like curve. It's like a roller coaster track in space-time that eventually leads you back to where you started, in both place and time. Some spinning black holes, according to the equations, might allow this. Of course, we haven't observed this, and most physicists believe reality prevents it in ways we don't fully understand. But the possibility remains that time is not a line, but a curve. That deep in space, far from our gaze, some particle or pulse of light may already be running in reverse. And here's the soft twist. If time loops back, would anything even notice? Would you? Could memory survive such a turn? In a place where time folds, maybe memory becomes the only compass. And maybe forgetting is a kind of safeguard, built by the universe to protect the story. These ideas may never be proven. But in this quiet moment, beneath blankets and starlight, they're a reminder. Time isn't linear. It's personal, flexible, and possibly reversible. What happens then if you leave time entirely? What lives outside of time? This question doesn't come with a clock. If something exists outside of time, what would that feel like? No before, no after, just is? In some theories of physics, like quantum gravity or certain string models, there is no universal time. The equations work fine without it, which is haunting because we live by time. We wake to alarms. We celebrate birthdays. We mourn what passes. Time gives shape to memory and meaning to change. But if time is not fundamental, if it's an illusion of perspective, then maybe space itself is more permanent than the moments we count within it. Some physicists argue that time emerges from entanglement, from relationships, not clocks. In this view, time is what allows change to feel real. But beneath that change, at the smallest level, there may be no ticking, just connection, just stillness, a web, not a timeline. And maybe that's what the deep silence of space teaches us best. In the cold, in the dark, in the long, slow nothing, something still persists, something that doesn't tick but listens, doesn't age but witnesses. What lives outside of time may not be something far away, but something already inside you, that deep stillness when everything else fades. Ahead in this video, we'll drift further into time's illusions and what they might reveal about everything we call real. A clock ticking near a star. Imagine placing a wristwatch on the surface of a star and then walking away with a second watch strapped to your arm. At first glance, they might look identical. Same ticking, same hands sweeping across the face. But in the presence of immense gravity, something subtle begins to happen. Time bends, not visually, not musically, but in the quiet ticking of reality itself. One clock drifts behind the other. It's not broken, it's obeying the rules of deep space. Einstein once suggested that gravity isn't just a force, it's a shape, a warping of the invisible fabric we live in. And the deeper you are in that fabric, the slower time moves for you compared to someone higher up. This isn't science fiction. It's been proven with atomic clocks aboard planes, satellites, and mountaintops. Time doesn't tick at the same speed everywhere. It never did. It only feels that way because we've always lived in one narrow layer of reality. So what happens when a clock sits near something massive, like a star, or even more so, a neutron star? The gravity is so intense it slows time dramatically, not in a way you'd notice by looking, but measurable in millionths of a second, a cosmic delay barely visible, but utterly real. If you stood there long enough, your own timeline would begin to fall behind the rest of the universe. This idea, that time itself slows down near gravity, changes how we think about the cosmos. Two people standing 1,000 kilometers apart might be aging at slightly different rates. A GPS satellite must constantly adjust for this, or your phone's location would be wrong by miles. Time is elastic, and in space it stretches more than we ever thought. And what about memory? What if the memories formed near intense gravity are somehow slower? What if consciousness bends too, just slightly? We don't have all the answers yet, but the more we learn about clocks near stars, the more we realize we've been standing on a curve in time all along. The infinite patience of black holes. Black holes. They don't spin fast in the way we think. Their surface, if you can call it that, might twist 100 times per second, dragging space itself in a whirlpool. But inside, it's another story. Time near a black hole doesn't rush. It doesn't even flow. It waits, stretches. Sometimes it barely moves at all. A spaceship hovering near a black hole's edge might survive for a few hours, maybe days by onboard calculation. But for someone watching from far away, that same ship would appear frozen, unmoving, as if trapped in amber. Its lights would fade, its signals would stretch out, and eventually it would vanish, not into the hole, but into slowness itself. This isn't just poetic, it's physics. At the event horizon, time slows to an almost complete stop relative to the universe around it. For the falling astronaut, nothing feels wrong. But to us, it's like watching the slowest sunset, one that never ends. The astronaut never really disappears. She just slows until her last visible moment becomes eternal. This isn't the end of her, of course. Beyond the horizon, her time continues. But that's beyond what we can ever measure. Our world obeys the clock, but the black hole doesn't. It listens to something older, slower, deeper, a kind of patience no human mind can truly hold on to. The illusion here isn't that time is playing tricks, it's that we expect it to behave the same everywhere. Near black holes, time turns inward. It curls around mass like fog around a mountain, and all we can do is imagine what it feels like to wait that long, to fall, forever. Starlight that left before you were born. When you look up at the night sky, you're not seeing the present, you're seeing the past. And not metaphorically, literally. Each glimmer, each tiny dot is a message from a different year. Some stars sent their light a decade ago, some 1,000, and some when the first humans had yet to take shape. The stars don't wait for us. Their light travels at a constant pace, 299,792 kilometers per second. But space is vast, and their stories take time to arrive. That twinkle you see tonight? It may no longer exist. That star may have exploded long ago. Its light just hasn't caught up with the truth yet. And so, we live inside a cosmic delay, a shimmering, beautiful lag that paints our sky with ancient memory. When you wish upon a star, you're whispering to something that may have burned out long before your name was ever spoken. And somehow, that makes the moment more beautiful, not less. If time is a river, starlight is the glitter on its surface, dancing in loops and swirls that tell us how far the water's travelled. Each telescope we build is a time machine reaching farther back into history. When we peer deep enough, we can see the birth of galaxies, the first sparks of cosmic dawn. The night sky isn't just decoration, it's the oldest record we have, and it's still updating, slowly, patiently, star by star, second by second, a delayed conversation between light and eyes, stitched across time. Galaxies that shouldn't exist yet. There's a puzzle quietly unravelling in the farthest parts of space. Telescopes, like JWST, are finding galaxies that look too mature, too large, too bright, too complex, and far too early. According to what we thought we knew, they shouldn't exist yet, but they do. Some of these galaxies appear just 300 million years after the Big Bang. But they behave like they've had billions of years to evolve. Stars already formed, dust clouds already swirling, shapes already settled. How did they grow up so fast, when the universe was still wiping the sleep from its eyes? Scientists are puzzled, but intrigued. Maybe our models need tweaking. Maybe time flowed differently in the early universe. Maybe gravity moved faster than we imagined. Or maybe our idea of cosmic infancy needs a rewrite. What if the early universe wasn't slow, but roaring with speed and hidden structure? This isn't the first time time has tricked us. Every time we build a better lens, the past looks stranger. The light from these galaxies took over 13 billion years to reach us. But what we see in that light doesn't quite match our clock. It's as if the universe built a library in record time and forgot to leave instructions. The illusion of time in deep space isn't just poetic, it's technical, it's observational, it's in the numbers. And every discovery that doesn't make sense makes the story even more worth telling. The twins who aged unequally. It begins as a thought experiment. Two twins. One stays on Earth, the other climbs into a spacecraft and zips away at near the speed of light. Years pass. The twin on Earth grows older. Wrinkles, birthdays, memories. The one in the ship returns and hasn't aged nearly as much. This is the twin paradox. Not a contradiction, but a strange truth of special relativity. The faster you move through space, the slower you move through time. And while both twins feel time passing normally, the one who moved, who travelled, comes home younger. We've tested this in smaller ways. Atomic clocks on planes, satellites in orbit. Time ticks just a little slower up there, enough that your phone's GPS has to compensate every day. Without Einstein's equations, Google Maps would never work properly. The future bends differently depending on how you move through space. But the idea of the twins, that's the one that sticks, because it's personal, emotional. Two siblings, two lifelines, reunited but not in sync. It touches something deeper, a sadness maybe, or wonder, that the universe doesn't promise fairness. It only promises math. And math doesn't care about goodbyes. In deep space, this paradox plays out constantly. Time moves at different paces all across the cosmos. And somewhere out there, someone's twin is still younger than they should be, still catching up, still returning from a future we can't quite understand. 11. The twin who stayed behind. Imagine two twins, born seconds apart, growing up side by side under the same roof, laughing at the same jokes and staring up at the same sky. But one of them becomes an astronaut. She leaves Earth on a high-speed voyage across the stars. When she returns, decades may have passed for her sister, while only a few years ticked by on the spacecraft. How can two people experience time so differently when all they did was move at different speeds? This is Einstein's twin paradox, and while it sounds like science fiction, it's a very real part of our universe. When you move close to the speed of light, time slows down, not just as an illusion, but physically, measurably. Your heartbeat, your breathing, even your aging, it all stretches out. Meanwhile, someone standing still in the universe ticks on at a normal pace. The faster you go, the more time bends around you. It's like stepping into a secret lane where the clocks run differently. And here's the twist. Neither twin actually feels time differently. To the one on the ship, life feels totally normal. She sips coffee. She reads books. But back on Earth, time is sprinting ahead. The illusion isn't that time has changed, it's that your personal path through time has curved ever so slightly. In space, time is not a single river. It branches, it bends. It can trick even the most grounded heart. When the astronaut returns home, she's younger, not just in spirit, but in years. Her sister may have grandchildren now. Her hair is grey. She has memories the other never lived. And both of them are right. Neither one travelled through time, they simply experienced different curves of it. And once again, time reminds us that it isn't fixed, it's felt. So when we imagine travelling far from home, not just through space but through time, we must ask not how fast we can go, but what kind of life we want to return to. Because in the universe, distance isn't just measured in kilometres, it's measured in memories missed. 12. The clocks that drift apart. We often think of clocks as truth-tellers, silent keepers of the moment. But even the most precise clocks begin to disagree, not because they're broken, but because they're honest. Place one clock on a mountaintop and another at sea level, and over time they'll tick at different rates. Gravity, it turns out, has a quiet influence over time. In stronger gravity, time slows just a little. It's not enough to notice during breakfast or traffic, but it matters to satellites and space missions. The GPS in your phone wouldn't work if scientists didn't correct for this effect. Your location depends on tiny disagreements between fast-moving space clocks and slower ones on Earth's surface. All because gravity tugs time inward. This is called gravitational time dilation, a gentle warping of time caused by massive objects. The more gravity you feel, the slower time flows. It's not broken, it's bent. Even astronauts aboard the International Space Station experience time slightly differently than we do on the ground. Their clocks stretch, just a little, with each orbit around the Earth. In deep space, far from stars or planets, clocks tick a little faster, but near a black hole they nearly freeze. 1,000,000 moments can pass out there, while near the event horizon, time whispers by. You could watch the whole life of a star unfold in the sky while sipping a single cup of tea, if you were sitting on the edge of that invisible well. So when you look at a clock, remember it's not just measuring time, it's measuring where you are, how fast you're moving, and how deep you are in the folds of the universe's gravity. Clocks don't lie, but they do whisper secrets. 13. Your feet are older than your head. If you're lying down right now, perfectly still, your body is experiencing time as a single whole. But if you were standing upright, something quiet and strange would happen. The atoms in your head would be aging faster than the ones in your feet. It's not a joke. It's physics. Gravity pulls harder the closer you are to the center of the Earth, and that slight difference, even a few feet, changes how time flows. Scientists have tested this using ultra-precise atomic clocks. Raise one clock just a meter off the ground, and it ticks measurably faster than the one below it. Our bodies don't notice it, but time is stretching and squeezing in microscopic ways every second of the day. Think of it like being on a slope. Even the tiniest change in height means the river of time flows at slightly different speeds. When you take a walk, when you climb stairs, when you fly in a plane, you're gently shifting your place in the timeline. It's so subtle that we never feel it, but it's always there, woven into the shape of your life. Now imagine this difference magnified across a mountain, or an orbiting satellite, or the edge of a neutron star. What's a hair's width of time to us becomes minutes, years, centuries to the universe. Our heads are always reaching ahead, our feet holding us gently to now. This realization can be grounding and humbling, because it means you are not just passing through time, you're sculpting it with your height, your position, your choices. Even your breath has a rhythm that the universe quietly keeps. 14. How time slows near the speed of light. In the everyday world, time feels reliable. Your coffee cools, your shadow shifts, the day turns to night, but step into a spacecraft, point it toward a distant galaxy, and accelerate to near the speed of light. And something happens. Time begins to slow, not just around you, but inside you. Your heartbeat slows, your thoughts stretch, and yet everything feels normal. This isn't science fiction, it's special relativity. At high speeds, especially those nearing the speed of light, time warps. The faster you move, the less time you experience. What feels like days aboard your ship could be centuries for those you left behind. Time doesn't just bend. It stretches across velocity like taffy pulled in silence. In that speeding ship, you don't notice anything strange. The walls feel solid. Your tea steams just right. But look outside and the stars blur. Light distorts. And if you could see Earth again, it might be unrecognizable. The cities you knew have grown old. Maybe they're gone. Maybe a new species looks up at the stars and wonders if anyone's out there. This concept isn't just poetic, it's practical. It's how future interstellar travel might work. If we ever journey to other star systems, we'll have to make peace with the idea that we may never return to the world we left. Not because we die, but because time has drifted too far. So when you imagine going fast, truly fast, ask yourself not just where you'll arrive, but when. Because at the edge of light speed, time is not a companion. It's a trail you leave behind. 15. Why time is different on the moon. The moon is our neighbour, a gentle grey companion drifting silently around our Earth. But even there, time dances a little differently. On the moon, there's less gravity. And where there's less gravity, time speeds up. If you lived there, you'd age a bit faster than your twin back home. Not by much, just microseconds each year. But still, it's real. Apollo astronauts experienced this difference. Their missions, though short, placed them in a slightly faster lane of time. They walked on a surface where clocks beat just a hair more quickly, where gravity's grip was lighter, where time had a looser hold on every step. Future moon colonies may need to correct for this. Communication, navigation, even birthdays. If you want to celebrate at the exact same Earth second your loved one does, you'll need to account for the time drift. It's tiny now, but it adds up, like soft snow on a quiet path. This is why space agencies build their systems with time dilation in mind. Whether it's the Moon, Mars, or deep orbit, time is not universal. It's personal. It follows the rules of mass, motion, and location. The moon may look timeless in the sky, but her heartbeat is ever so slightly out of sync with ours. And so, when you look up at her, bright, round, and slow, know this. She's not just far away in space. She's a few ticks ahead in time. And the further we go, the more we drift. The clock that floated too far. Imagine placing a clock at the edge of a gravitational well, and another clock drifting far from any planet or star, both ticking, both seemingly identical, but only one keeps time as you know it. Gravity doesn't just bend light, it stretches time. Einstein's theory of general relativity tells us that time runs slower in stronger gravitational fields, so a clock resting at the base of a mountain ticks ever so slightly slower than one at the summit. It's imperceptible in daily life, but in space the illusion becomes poetic. Astronauts orbiting Earth experience this daily. Satellites, GPS systems, all must account for time dilation to remain accurate. Yet the deeper we move into the cosmos, the more this stretching becomes surreal. In places where gravity is immense, near neutron stars, black holes, clocks behave like dreams. Now imagine a spacecraft falling toward a supermassive black hole. To the outside world, it appears to slow down, pause, and never quite arrive. From within, time feels normal, continuous, almost deceivingly gentle. This dual perception creates a paradox, a floating clock lost in interpretation. And in the spaces in between, where gravity fades and expands, time takes on a quiet rhythm, not a beat, not a pulse, but a slowing breath of something older than timekeeping itself. Where time goes missing. Deep within galaxy clusters, there are regions so vast, so quiet, that time begins to feel like a suggestion rather than a rule. Out in cosmic voids, those enormous black stretches between galactic superstructures, there is very little matter and therefore very little gravitational pull, which means time flows faster there, faster than near Earth, faster than around stars, faster than you or I could ever experience. If someone lived in one of those voids, if life could survive there at all, they would age more quickly than us. Not because they move faster, but because gravity isn't pulling their seconds as tightly. But here's the mystery. How would they ever know? Would the stars they see appear younger? Would the universe seem more active, more youthful, more hurried? Or would it all feel perfectly normal? Time doesn't announce its pace. It quietly changes depending on where you are without you realizing it. In this way, cosmic voids are like forgotten chambers in a cathedral, where time drifts softly upward, uninterrupted, unnoticed, but very much changed. Galactic timekeepers. Galaxies are not just collections of stars. They're also the ticking hands of the universe's vast clockwork, spirals that rotate, ellipticals that wobble, irregulars that shimmer in disarray, all slowly marking time not in seconds, but in billions of years. A galaxy's rotation can tell us about its age. Its shape can hint at collisions long ago. Its movement can whisper secrets about the fabric of the cosmos itself. But galaxies are also deceivers. Some galaxies we see are already gone, their light only now arriving after a journey of millions or billions of years. What we observe is not their present, but their ghost. Time, again, refusing to be straightforward. Even our own Milky Way is rotating. But so slowly it would take 225 million Earth years to complete just one turn. So what year is it? Really? What frame do we use when everything is spinning on a different rhythm? Galaxies remind us that the universe keeps time, just not one we can wear on our wrist. The star that lived in two times? Light from a single star can split time into two experiences. When astronomers look through powerful telescopes, they often see a star twice. Same star, different positions, even slightly different ages. Why? Gravitational lensing. A massive galaxy or black hole bends the path of light behind it, acting like a lens, magnifying and duplicating what lies beyond. Sometimes that means the same star appears in two or more places at once, each image arriving from a different path, each path taking a different amount of time. So we witness the same object at two moments in its own past. One star, but two versions of its story. Frozen in light, yet flickering between timelines. It's like seeing your reflection in a mirror and a photograph at once. Both are you, but one has already happened and the other is still on its way. This cosmic illusion isn't a trick. It's just the universe showing us how time folds with light and plays quietly in the in-between, where time loops like a whisper. And now we reach a stranger question. Could time, under the right conditions, loop? Not metaphorically, not in memory or emotion, but physically, bending around on itself like a ribbon in gravity's hands? There are theories, soft, speculative, that suggest this is possible. In regions around rotating black holes, called Kerr black holes, the intense spin and curvature may allow for closed time-like curves, which is science's cautious way of saying, maybe, just maybe, time can curve back. What would that feel like? Would you relive a moment? Would you even notice? Or would the loop only reveal itself much later, as a déjà vu of stars? There's no evidence we found such a loop, but mathematics hasn't ruled it out either. And in deep space, where illusions become norms, the very idea of a looped timeline seems less like fiction and more like possibility, waiting patiently to be discovered. Ahead in this voyage, we'll drift even deeper into the illusion, toward the silence where beginnings and endings blur, echoes that arrive out of order. If time were a simple straight line, we'd always hear echoes after the sound. But in deep space, things aren't so polite. Light from distant galaxies doesn't arrive in neat packages. You might witness the aftershock of an explosion before the light of the star that caused it. It's not fantasy, it's delay. Distance doesn't just stretch space, it messes with the order of events. A supernova can greet your telescope long after its light left a dead star behind. Out here, you're not always seeing things as they happen. You're seeing things as they once were, and not always in sequence. Even radio signals, the kind we humans send out into the void, become time travelers. A whisper from Earth in 1977 is still floating out there, unnoticed, toward a corner of the galaxy that hasn't yet met disco music or Cold War paranoia. But here's the twist. If an alien civilization were to hear that signal decades from now, they'd be listening to our past in their present. That makes you wonder, what signals are reaching us now that were sent before Earth even existed? Whose past is overlapping with our moment? It's tempting to think of telescopes as time machines, and they are in a very real way. When we point them at Andromeda, we're looking back over 2 million years. The light we see tonight began its journey before humans had language. So when astronomers witness changes in deep space, they're often playing cosmic archaeologists, brushing dust off scenes that no longer exist in the present moment. That delay creates illusion, a beautiful one, and it paints the sky with ghosts we can still study. We sometimes see galaxies colliding, but the collision already happened, millions or even billions of years ago. The shape, the flash, the stretching arms of starlight we admire. They're long gone in real time, but still arriving in pieces to our eyes. The event is over, but the light hasn't finished telling the story. In this way, the cosmos is never truly live. We are forever a few steps behind the dance, and yet, somehow, it still feels like we're part of it. Out in deep space, you don't always get a timestamp with your view. Things echo, things loop, things appear before their causes do. It's like reading the ending of a book before knowing the main character's name. But strangely, the more you understand this cosmic delay, the more you realize. Time, out here, is not just stretched, it's scattered. And every scattered echo is a reminder that what you're seeing might already be gone, but its story still matters. A clock that ticks too fast. Time doesn't just slow down in deep space. Sometimes it speeds up. At least that's how it feels when you look far out into the expanding universe. Galaxies at the edge of the observable cosmos aren't just receding from us. They're racing away so fast their light is redshifted beyond ordinary view. But something strange happens when you analyze the photons. The ancient light pulses arriving from those galaxies seem to beat faster than they should. They tick like hurried seconds, skipping like a broken watch. It's not because they're rushing, it's because the fabric of space itself is stretching as the light travels. The beat of time recorded in that light, like flashes from a pulsar, gets distorted. Our instruments try to measure regular intervals, but the further the source, the more stretched and uneven the rhythm becomes. We're not seeing their time as it is, we're seeing their time as it was, stretched by our own cosmic motion. What was once a perfect pulse becomes a smeared memory. This isn't just academic curiosity, it affects our models of the universe. When scientists estimate distances and ages, they have to account for how much time appears warped. Some galaxies may look younger than they are because their clocks seem to tick too fast. Others may seem older, slowed down by gravity wells we don't yet fully understand. In the grand measurement of the cosmos, every tick and tock must be filtered through a warped lens. And then there's us, the observers. We think of ourselves as standing still, but we're not. The Milky Way is drifting, the solar system is rotating, Earth is spinning, and we're swaying along for the ride. So our frame of time is moving too. Like someone trying to measure a dance while already dancing, we're constantly trying to understand time while caught in its current. That alone should make us pause, just for a moment, and listen. So when a star seems to flicker too quickly, or a galaxy feels oddly rushed, remember, it's not the universe that's frantic. It's that we're watching time from a moving ship. And depending on where we look, how far we reach, and what paths those photons took to arrive, we may not be seeing time as it is, but only as it once tried to be, planets that forgot to spin. On some distant worlds, time doesn't flow in days. It lingers. It stalls. Imagine a planet where one side always faces its sun, where daylight never ends, and night is a distant memory on the other half. These are tidally locked planets, and they're not just theoretical. We've found them. One side scorched, the other frozen. And in between, a thin strip where time might still feel like home. With no sunrise or sunset, how would time feel to the beings who live there? If they exist? Would they even invent the concept of hours? Would a shadow ever move across their sky? For us, time is measured by movement, the ticking of a clock, the rising of the moon, the passage of seasons. But on a planet that doesn't spin, what marks the passing of a moment? Strangely, these planets can still be habitable in the twilight zone between the hot and cold extremes. Some scientists even speculate life might emerge in those balanced bands, where temperature is stable and winds circulate evenly. But that life would evolve under stillness. It would not grow with morning and night. Its biology, its sleep, even its memory, would be shaped by eternal dawn. What kind of civilization would this create? Would they value time the way we do? Would they fear change or crave it? Or would they see time as something internal, not tracked by shadows, but by thoughts and feelings alone? The absence of planetary spin doesn't stop time, but it changes how time is felt. And feeling time is what truly makes it real for us. So next time you see a planet listed in a distant solar catalogue marked tidally locked, don't assume it's dead. Don't assume time stands still there. Just imagine a world with no ticking clocks, no rotating skies, no rush to begin or end the day. Just the endless quiet hum of time held in place. The great pause between galaxies. In the vast stretches of intergalactic space, those frozen voids between clusters of stars, time doesn't really stop, but it does seem to hesitate. There's no gravitational pull strong enough to bend it, no massive star to quicken it, no black hole to stretch it thin. It simply glides. The rate of time in these quiet places is different, not faster, not slower, just paused in a way that defies ordinary rhythm. Imagine floating between galaxies. Nothing pulls on you. No light arrives for years. No sound. No change. In that eerie stillness, you might lose your sense of hours or days. Your heartbeat could be the only clock you know. These are the true deserts of the universe, not because of heat, but because of time's absence of texture. Smooth, featureless, suspended. But even in these voids, photons travel, and they carry time with them, so the space is not empty of time, just empty of things that feel time. Without events, without gravity, without friction, time becomes like glass, invisible, yet there, waiting. It's in these forgotten corridors between stars that the illusion of time becomes most haunting. Strangely, this absence helps shape everything else. It gives structure to the motion around it. The galaxy spins faster because the void is slow. The stars burn brighter because the backdrop is dark. Like silence in a symphony, the stillness between galaxies makes everything else sing. In this way, emptiness gives time its rhythm. So the next time you imagine the universe, don't just picture stars and planets. Picture the spaces between them, the ones where time barely whispers. Because sometimes the deepest truths hide not in motion, but in stillness, too complete to describe. Moons that never see midnight. Imagine a moon orbiting its planet so closely that its day is forever chained to the same face. One hemisphere bathes in starlight, the other never sees it. But unlike a tidally locked planet, this moon's time isn't its own. It dances to the pull of its parent, swinging around in rhythms more ancient than calendars. These moons don't choose their time, they borrow it. Many moons, like ours, rotate in harmony with their orbit, but others, like the chaotic moon Hyperion, tumble wildly, caught in gravitational crosswinds. One moment, their poles point one way, the next they twist. For inhabitants, if any exist, time would feel unstable. Midnight might never arrive the same way twice. And then there are moons like Europa and Enceladus, frozen on the outside, but with oceans beneath. Beneath their icy crusts, tidal forces from their planets churn warmth into their cores. There, time is measured not by sunlight, but by the stretching and squeezing of rock. Their clocks are geological. Their heartbeat is heat. Would life down there know night from day? Would it matter? Deep in those oceans, time flows without sunrise, without weather, without seasons. Movement is slow, change is deep, and yet things live, or might, and their sense of now would be utterly alien. So while we often look to planets for time stories, don't forget the moons. They're not just satellites, they're time travelers. Carried, twisted, shaped by gravity's pull and silence's patience. Some never know midnight, some never know noon, but they all know motion, and that motion writes time in ways we're only just beginning to read. The ticking clock. Beneath the ice, somewhere beneath the icy crust of Europa, Jupiter's moon, There may be oceans, deep, dark, and untouched by sunlight for billions of years. But here's the question. If time moves slightly slower in Jupiter's powerful gravitational grip, how would that affect life if it exists there? Would a microbe under that ice age at a different pace than one floating in Earth's shallow tide pools? It sounds like science fiction, but it's not. Time dilation is very real, and it doesn't care if you're aware of it or not. If we imagine a world sealed off from sunlight, gravity becomes the loudest voice in the room. Europa is small, but rests in Jupiter's immense gravitational field. That tug, gentle from far away but monstrous up close, bends both space and time just slightly. The seconds tick a little slower than they do for you here, reading this sentence on Earth. That delay might only be fractions of a second over a century, but still. It's enough to shift the rhythm of an ecosystem if one ever pulses down there. Now take a creature, a hypothetical one, something like a bioluminescent shrimp, and imagine it's lived under Europa's ice for 100 million years. Not just hidden from sunlight, but tucked inside a slow-moving pocket of time. Would its biology evolve differently? Would its cells divide at an imperceptibly slower pace? Would it experience memory, motion, or metabolism in a tempo unique to its world? These are not philosophical questions. They are biological mysteries waiting in orbit. The ticking of time beneath that ice is so faint, so patient, that it's easy to forget it's still ticking at all. But it is. Every second on Europa is slightly stretched, like warm taffy. If you were to land, live, and return, you'd bring with you a time signature different from anyone else on Earth. You wouldn't feel it, but your molecules would quietly remember it. Space doesn't need your permission to stretch time. And that's what's so quietly poetic about deep space. Time is not universal. It's personal. It's geographical. It's even gravitational. If Europa holds life, or even the memory of it, that life may have been moving to a rhythm not just slower, but older than our own. And somewhere in that icy slowness, time might not feel like time at all. Why photons never age? You've probably heard it before. Light travels fast. But what you might not know is that for a photon, time doesn't move at all. Not 1 second. Not even a blink. A photon could be born in the core of a star and travel for 10 billion years before it reaches your eye. And from its own perspective, that trip took no time at all. This strange truth is one of the most counterintuitive ideas in physics. In Einstein's theory of relativity, the faster you move, the slower your experience of time becomes. And light, the fastest thing in the universe, doesn't experience time passing at all. It doesn't age. It doesn't grow tired. It simply exists. So what does that mean for the light we see in the sky? That beam of starlight you admire from your backyard could have been travelling since the dinosaurs walked the Earth. But for the photon, the moment it left its star and the moment it hit your retina happened simultaneously. For it, there is no before or after. No journey, just one unbroken instant, a flash suspended in forever. This creates a strange tension between us and the light we live by. We are creatures who age, worry, remember. We live in time, but light does not, and yet we are made of it. Our biology relies on it. Our eyes interpret it, and our memories, our most sacred timeline, are built entirely from the things we've seen. So we are stitched together by something that, in a sense, never moved through time at all. So when you gaze at a star tonight and marvel at its ancient glow, consider this. You're not just seeing into the past. You're touching something that, from its own perspective, never left the present. Galaxies moving without motion. In the far reaches of the universe, entire galaxies appear to be racing away from us. Faster and faster, the farther they go, And yet they're not really moving at all, not in the traditional sense. It's not the galaxies that are travelling, it's space itself that's expanding, which means time is stretching too, and that changes everything we thought we knew about distance, speed, and even memory. This phenomenon is called cosmic expansion, and it's not like an explosion from a central point, it's more like dots on a balloon moving apart as the balloon inflates. The galaxies are stationary in their own space, but the space between them is growing. And that expansion isn't just a physical stretching, it's a temporal one. It distorts how we see, how we measure, and how we remember the cosmos. Light travelling across this expanding space gets stretched too. That's why the farther away a galaxy is, the redder its light appears. It's not just older, it's more diluted, more distant in meaning. That red shift isn't only a measurement of speed. It's a soft whisper that time is loosening its grip the farther we look. And yet, in a strange paradox, that very stretching of space and time allows us to glimpse the past with almost impossible intimacy. When we look into the deep field, we're not seeing what the universe looks like now. We're seeing baby pictures, cosmic echoes frozen in their infant forms. The light is old, the space is wide, the time is tangled. So when we say a galaxy is 10 billion light-years away, we're not describing its position now. We're describing a memory, a snapshot, a whisper from a younger cosmos, floating gently across a universe that keeps unfolding. The future already exists. Maybe. Time feels like it flows forward. One moment leads to the next, like footsteps. But in some interpretations of physics, especially in Einstein's equations, the past, present, and future all exist at once. They're not moving. We are. You are a traveller across a landscape of time that already exists in full. So, what does that say about your future? This idea is known as the block universe. It suggests that the universe is like a frozen four-dimensional loaf of space-time. Every event, every breath, every heartbeat, every supernova is set in the structure. Not because it's predetermined, but because it's already there. You're not being pushed by time, you're tracing a path through it. From your perspective, time feels like change, like choice. But from outside the block, if such a perspective were even possible, there would be no change at all. Just a still, complete sculpture of everything that ever happened and ever will. Does that mean the future is fixed? Not necessarily. It may be better to think of it as already existing in potential, not certainty. It's a deeply philosophical concept, and one that divides scientists and thinkers alike. But it opens up a new way of seeing your life. If time is not a river, but a landscape, then your memories are just as real as your future, and perhaps even as reachable. So when you wonder where you're headed, or who you're becoming, you might consider that version of you already exists somewhere in the soft geometry of space-time, waiting to be noticed. When clocks disagree, not all clocks tick at the same speed, and in the universe, this isn't a mechanical error, it's a feature. Time itself is relative. Gravity, velocity, and even altitude can change how quickly your seconds pass. A clock on the top floor of your building ticks slightly faster than one on the ground. And a satellite in orbit? It ticks differently too. This isn't theory. It's tested, measured, and quietly corrected every day. GPS satellites, for instance, operate in a slightly different time stream than we do. If we didn't account for time dilation, your phone's map would become wildly inaccurate within hours. Space bends time, and we build our technology around that bend. It's a humbling reminder that time is not absolute. It's flexible, local, personal. Your heart may beat the same as someone else's, but your seconds may not stretch exactly the same way. Not if one of you is flying, climbing, or orbiting. Time bends gently, invisibly, with motion and mass. This raises profound questions. If two people experience slightly different time streams, are their memories shaped differently too? Could tiny discrepancies in time create vastly different emotional timelines? Does living at higher altitudes stretch your life, even slightly, in more than just metaphor? In a universe where even your wristwatch disagrees with the sky, time reveals its true nature. Not a metronome, but a fabric, one that folds, stretches, and quietly disagrees with itself, all while keeping the illusion that it's ticking in unison. Time slows down in the shadow of giants. In deep space, not all gravity is created equal. When you drift near a massive object like a black hole or neutron star, something strange begins to happen. Time itself doesn't behave the way we expect. It stretches, it dilates. To someone far away, you begin to slow down, almost like a moving memory stuck in slow motion. But for you, everything feels normal, and yet everything around you continues forward without you. The deeper the gravity, the slower your clock ticks. This effect, known as gravitational time dilation, is not just theoretical. It's been measured. It's real. Even GPS satellites above Earth have to correct for it, or your maps would be off by miles. Imagine that. Your phone knows about relativity before you do. But in the deep cosmos, this effect isn't just a correction, it's a transformation. Around massive celestial bodies, 1 second could mean days, years, or even centuries to someone watching from afar. If you floated close to the edge of a black hole, just before the event horizon, your body would still move, your heart would still beat, and your thoughts would still form. But to a distant observer, you'd appear frozen, locked in a moment, a statue of light and memory held by gravity's soft prison. They'd never see you fall in, just pause, forever, as if time itself gave up trying to follow you. This idea can feel unsettling at first. The notion that you could be alive and thinking while the rest of the universe surges forward without you. But in a way, it's also beautiful. A quiet reminder that time isn't absolute. It bends, it listens to gravity, and sometimes it whispers instead of shouts. And maybe that's the deeper message of time near giants. That slowness isn't always stillness. That existing quietly in the arms of gravity is still existing, even if the rest of the universe has moved on. The ticking clock of light beams. Imagine holding a tiny clock in the palm of your hand, but instead of gears and springs, it uses light. A beam bounces between two mirrors. Tick-tock, tick-tock. Every time it hits the top or bottom, a second passes. It seems simple, until you start moving through space. Then something astonishing happens. That beam, which once moved straight up and down, begins to tilt sideways. Because light always moves at the same speed, even when you're in motion, the beam must travel a longer path between ticks. This longer path means it takes longer to hit the mirror. Your clock slows down. This is time dilation again, but this time from motion alone. It's not just about gravity, it's about speed. The faster you go, the slower your time becomes. This is the reason why astronauts who spend time orbiting Earth at high speeds actually age a tiny bit less than the people down below. It's only a few milliseconds, but it's measurable. And in deep space, if you were to travel at 90% or 99% the speed of light, the effect wouldn't be tiny anymore. Entire years could pass for others, while only a few days pass for you. It's a humbling reminder that time isn't a single universal beat. It's deeply personal. Two people can leave the same moment and return to two different futures, just because they moved differently. That's not science fiction. That's relativity. And it's happening right now in every satellite, every spacecraft, every tiny beam of light bouncing through the cosmos. And maybe in the end, time is just another kind of traveller, moving faster, slower, bending and folding, not to confuse us, but to invite us deeper into the mystery. Time isn't always in a straight line. We like to think of time as a straight road. You wake up, you eat breakfast, you go to sleep. One thing follows another in a perfect line, but in deep space, under the influence of massive stars and swirling galaxies, that road begins to curve. Sometimes it even folds back on itself. The closer we look at the universe, the more time begins to resemble a loop, a spiral, or a labyrinth. Einstein's equations suggest that time and space are part of the same fabric, and like any fabric, it can ripple, stretch, and curl. Around spinning black holes, time doesn't just slow, it twists. Objects falling in can follow strange looping paths where the direction of time becomes tangled. Imagine taking a step forward and ending up behind yourself. Some theoretical solutions even propose something called a closed time-like curve, a loop in space-time that lets an object return to its own past. These are mathematical, not physical certainties, but they force us to consider the possibility. Is time always forward moving? Or could it, under just the right conditions, fold like paper in a child's hand? In our daily lives, this seems impossible. But in the quiet, distorted regions near pulsars, neutron stars, or spinning black holes, space and time dance differently. They twist around each other like ribbons in wind, and sometimes that dance reveals paths we never imagined. The universe, it seems, doesn't favour straight lines, it favours curves, and in those curves, time hides possibilities we've only just begun to glimpse. A universe with different clocks. Let's take a step back. Think about Earth. Think about a clock in New York and one in Tokyo. They're both telling time. But because Earth is spinning, because satellites are orbiting, and because gravity varies slightly by location, those clocks tick ever so slightly differently. Tiny differences, measured in billionths of a second. But in deep space, those small cracks in uniformity widen. In the vastness between stars, gravity isn't constant. Some regions are calmer, others are pulled into gravitational tides. Each planet, moon, asteroid, even every passing particle has its own clock, its own rhythm, and none of them agree perfectly. Time here is not a single heartbeat, but a symphony of slightly misaligned instruments. This idea, called proper time, suggests that every object experiences its own timeline, and that means there is no grand cosmic clock ticking in the background, just a billion private journeys. So if you were drifting through space in a small pod, watching a pulsar blink in the distance, you'd be on your own time. Your seconds wouldn't quite match those of Earth or Jupiter or even your fellow astronauts far away. This idea reframes how we think about distance. It's not just space that separates us, it's time too. Every step across the galaxy isn't just movement, it's a step through a slightly different clock. In this way, the illusion of time isn't that it exists, but that it's shared. In truth, every moment is yours alone, ticking gently, somewhere far from everything else, falling into time's deepest well. Picture this. A star collapses. Its core implodes. A black hole is born. Space bends inward, and time bends with it. If you fall toward it, slowly, peacefully, you won't feel the twist. But time will. Your clock, the one on your wrist or inside your cells, begins to diverge from the rest of the universe. From far away, your fall looks frozen. The light from your body struggles to escape. It redshifts, fading into longer and longer wavelengths until it vanishes. But you're still falling, moving calmly, deeper into the gravity, deeper into the curve. Time stretches. Seconds become oceans. Inside the event horizon, the roles of space and time switch. What was once your freedom to move becomes a one-way path. The future becomes a destination you can't avoid. You don't move toward the center. You are pulled through time toward it, as if time itself is collapsing with you. This is where physics becomes poetry. We can't fully describe what happens inside a black hole, but the math suggests that time no longer behaves like time. It may stop. It may loop. It may become something else entirely. And yet your consciousness, your awareness, may never notice. You're still falling, still thinking, still being, in a place where time no longer flows. Falling into time's deepest well isn't about endings. It's about transformations. In deep space, even the death of a star gives birth to new ideas about what time might actually be. The time-tangled heart of a pulsar. Imagine a lighthouse spinning in the dark, not on the ocean, but floating in the emptiness between stars. That's what a pulsar is. A dead star collapsed into something unimaginably dense, spinning hundreds of times per second, shooting out beams of radiation like cosmic spotlights. But what's stranger than its speed is its time. For pulsars, time is not just marked by rotation, it is encoded, sculpted, and flung outward in perfect pulses that echo across the galaxy. Some pulsars keep time more precisely than atomic clocks on Earth. They tick in silence, never missing a beat, even after millions of years. And yet they were born from catastrophe, the death of a massive star. Their clocks began in chaos, but somehow settled into rhythm. You'd think something born from an explosion would be unstable, but here in deep space, time often finds strange ways to calm down, or pretend to. Now imagine you could ride the edge of one, not get pulled in, but hover just close enough to feel the gravity. Your own sense of time would slow to a crawl, while the world outside raced ahead. Meanwhile, a distant astronomer might measure your moments by those perfect pulses. You'd both be watching the same object, but from two different realities. And then there's the mystery of pulsar glitches, sudden tiny jumps in rotation speed, like a broken second hand lurching forward without warning. No one knows exactly why they happen. Maybe it's a starquake. Maybe the inside of the pulsar is shifting. Either way, for a cosmic clock to skip a beat, it suggests that even in deep space, time doesn't always play fair. Pulsars show us that time isn't always smooth. It can be cracked, it can be scarred, and yet, somehow, it still sings. Ahead in this journey, we'll meet another kind of timekeeper, one that doesn't spin at all, but instead expands. When time spilled from the Big Bang, before stars, before galaxies, before light, there was a moment when time itself began. Or maybe more accurately, there was a moment when time became meaningful. Scientists call it the Big Bang, but it wasn't an explosion in space. It was space itself, expanding, and with it, the first second was born. That first second wasn't like your seconds now. It was wild, hotter than anything we can imagine, packed with pure energy and potential. Time didn't tick, it roared. In a way, the universe was sprinting, racing outward, stretching every direction at once. But what did it stretch from? And into what? And if you had been there, in that newborn moment, assuming you could somehow exist, you wouldn't have recognized anything. No stars, no atoms, no ticking clocks, just expanding space. And time, unfurling like a scroll. It's easy to forget that time itself had a beginning, and that the very concept of before may not even make sense. Here's a strange thought. When scientists study the early universe, they talk about time in units so small they're almost imaginary. Planck time. 1/trillionth of a trillionth of a trillionth of a second. That's how fast things were changing. And yet now, Billions of years later, the universe has slowed down, softened, stretched thin and wide like old fabric. The Big Bang wasn't just the start of everything, it was the start of time being something you could count. Everything since then has been a conversation between energy, space, and time. And in the silence of deep space, the echoes of that first moment still ripple, still whisper, as we explore the illusion of time farther outward. Cosmic background light and the fossil of a second. Close your eyes and picture the afterglow of creation. A soft, invisible fog of microwave light, stretched so thin it's colder than ice, but still shimmering across the entire universe. That's the cosmic microwave background, the oldest light we can see. And it's a map of time itself. This light was born just 380,000 years after the Big Bang, when the universe cooled enough to let light finally travel freely. Before that, everything was a glowing soup, opaque like thick fog. But then the fog cleared, and light escaped, and it's still escaping, passing by us, gently whispering of a time so ancient it almost feels fictional. The strange part, that light you can detect today from your microwave oven is the same light from that ancient moment, just stretched, pulled by the expansion of space. It started out as searing radiation. Now it's a cold whisper. And in that stretching, we see time moving not in seconds but in wavelengths. Scientists have mapped that light into patterns, tiny temperature differences like ripples in a frozen pond. And those ripples are the seeds of everything: galaxies, clusters, you, me. All of it came from those quiet variations in ancient time, a time that never stopped expanding. So the next time you microwave leftovers, know that the same physics that warms your food is also how we study the beginning of time. And the glow that surrounds you, invisible but always present, is the most ancient story still unfolding. Do galaxies age, or just travel through time? Galaxies seem eternal, swirling islands of stars, glowing calmly in the night sky. But they're not frozen, they're moving, changing, aging. Some collide, some fade, some become giants, others shrink into shadows. But the real question is, how do they experience time? When we look at a galaxy a billion light years away, we're not seeing it now. We're seeing its past, its million-year-old face travelling toward us on a beam of light. So when we study galaxies, we're always looking backwards, always behind the curtain of the present, always through the illusion of delay. And then there's gravity. In dense galaxy clusters, time runs slower. Not by much, but just enough that clocks tick differently in the core than at the edge. A galactic ballet, choreographed across slightly different timelines. Does a star forming in the outer arm of a spiral galaxy experience time the same way as one near the black hole at the centre? Some galaxies have stopped making stars. Others are just beginning. Some are bursting with colour. Others glow faint red, cosmic retirement homes. Their stories are different, but all unfold within the same universe, governed by the same time but felt in different ways. So maybe galaxies do age, but not like we do. Maybe they bloom, drift, merge and fade across eons of stretched time. And as we keep watching them from our little corner of the cosmos, we realize something humbling. The deeper we look, the younger the universe gets. And the farther away, the older we feel. You are made of time that took the long way. If you could trace the atoms in your body back through time, you'd find a journey stranger than fiction. The iron in your blood was forged in the core of an exploding star. The calcium in your bones, born from stellar collapse. The oxygen you breathe, woven from ancient nuclear fusion. But these atoms didn't arrive quickly. They drifted, floated. They passed through gas clouds, clung to dust, danced in planetary rings before they ever became part of you. Every breath you take is borrowed from a process that began before Earth even had oceans. You are made of time, not just moments lived, but moments travelled. The carbon in you once floated in the body of a starfish, or a leaf, or a cloud. It journeyed across light years, waited in rock, slept in silence, until something, perhaps a supernova, scattered it again. And somehow, all those ancient particles arranged themselves into you, a being who can sit still, breathe slowly, and wonder about time. It's funny, isn't it? You're made of particles that don't even experience time the way you do. Particles that don't care about minutes or hours, just motion and interaction. So tonight, as you drift into rest, think of that. You are not just living through time. You are time, gathered, condensed, and conscious. You are the long way made whole, and still travelling.